All right. Hello, everyone. Good morning and welcome back. We are actually going to finish our, hi, Kevin. We're actually going to finish our guided notes for Unit 2 today. We only have a couple pages left, and I really do anticipate that we'll be able to finish these in this session, which is really cool, which means Monday I want to meet with you all in Zoom. All right. So let's take a look. We are going to continue with where we left off. In last class, we talked about literal equations. Basically, we were solving for the indicated variable in a sea of variables. So it's kind of interesting, kind of keeping in mind the fact that, as we move through these problems, we really wanted to focus on what is the opposite operation. Perform the opposite of what you see to isolate, to work your way towards isolating that variable. We're going to continue today by looking at ratios and proportions and finish off with similar figures. So let's take a look. Ratios and proportions. So let's define a ratio. A ratio is the quantitative relation between two amounts showing the number of times one value contains or is contained within the other. Okay. Hi, Johanna. The quantitative relation between two amounts showing the number of times one value contains or is contained within the other. So, for example, the ratio of, let's say, I don't know, lemons to limes is, let's do, I don't know, 3-to-1. Okay, so essentially for every 3 lemons, there's 1 lime. So the ratio of lemons to limes is 3-to-1. That's just an example. Notice here that ratios, how we're going to look at them, they'll be written in this form, A:B, where A and B are the terms of the ratio. So 3 and 1 are the terms of this ratio. I put a note here for all of you, and that's that ratios must be presented in the same unit of measurement. So if you have different units of measurement, then you want to actually do conversions so that they're the same unit of measurement. And then you want to make sure that they're in lowest terms. Notice here when I said the ratio of lemons to limes is 3-to-1, this is in fact in lowest terms. You might be thinking, wait a second, lemons and limes are not the same unit of measurement. Well, think again. A lemon is not a unit of measurement. A lime is not a unit of measurement. So essentially we're saying this set of objects to the other set of objects is 3-to-1. So I want you to think of it like that. But if you actually have units of measurement like feet, inches, days, hours, minutes, etc., you want to make sure that you're converting so that the units are the same. So let's take a look at an example. We have find the ratio of 4 hours to 40 minutes. What you may want to do here that I have found helpful is just kind of working through this baby steps is let's first start off by rewriting this as 4 hours colon 40 minutes. I'm going to take this in a step-by-step fashion in the way that I've seen very successful with students throughout the year. So step number 1 is making sure we rewrite it as a ratio using the colon. Okay, so here's our colon. Next, I want you to consider that we have 2 different units of measurement. We have hours and we have minutes. So we have to think about the relationship between hours and minutes. So you're probably thinking to yourself, well, the relationship is that in 1 hour, you have 60 minutes, right? That's the relationship. That's the conversion that you should use. Hi, Maria. So having said that, wouldn't it make sense to say, well, 40 minutes is part of an hour, So maybe I don't want to convert this to a decimal. I want to avoid that. So how about we say, well, how many minutes are in 4 hours? So I'm going to make a note here that says convert larger unit into smaller unit. So in 1 hour we have 60 minutes, in 2 hours we have 120 minutes, so in 4 hours we have 240 minutes. So now the cool thing about this is that it's very clear just by our labels that both of these terms have the same unit of measurement. So at this point, we actually don't need to include the minutes label. So they're the same unit of measurement. Now we have to reduce these. So if these are terms, it's a ratio. So think of it as like a quotient of two terms. I want you to consider that we can actually divide by a common factor. Okay, so think of it as like if you're reducing a fraction. So I'm going to write here, think 240 divided by 40, right? So we're going to reduce that. So right away, notice that the zeros will cancel because you could divide by 10. 240 divided by 10 is 24. 40 divided by 10 is 4. But also notice we can continue. Notice that we are able to divide each of these by 4. So 4 goes into 24 6 times and 4 goes into 4 once. So our ratio, and I'm going to make a note here, reduce, our ratio becomes 6:1. Okay, and that is a ratio in simplest terms. All right, we start off by rewriting using colon. We then convert the larger unit into the smaller unit. That's going to make life easier. And then once we have both of the units the same, we say, okay, let's reduce. In this case, we were able to reduce. I essentially wanted to walk you through this concept of thinking of it like a fraction. You could reduce a fraction all the way to lowest terms, and then we simply write our reduced ratio. So the ratio of 4 hours to 40 minutes is simply 6:1. Let's try that again to make sure that we're all on the same page. Next we have 15 feet. Let's move this in a little. 15 feet to 7 yards. The first thing we want to do is we want to consider, well, what is the relationship between feet and yards? If you said that in 1 yard there's 3 feet, then nicely done. Okay, step number 1, let's write it using the colon. So 15 feet colon 7 yards. That's step number 1. Step number 2, our larger unit, which is yards, needs to be converted into the smaller. We can actually convert the smaller into the larger, but just for the sake of consistency, I'm going to convert the larger into the smaller. So I'm going to write convert. And we know that in 1 yard there's 3 feet, 2 yards there's 6 feet, 3 yards there's 9 feet, while in 7 yards there's 21 feet. Okay, so we convert, that gives us 21 feet. Now the cool thing is we have 15 feet to 21 feet, so they're the same unit of measurement. Our next step will be to reduce. So you may want to look at this as a fraction and say, okay, well, if it's 15 over 21, right off the bat, I know I could divide by 3. So 3 goes into 15 5 times, and 3 goes into 21 7 times. So my reduced ratio is 5:7. Order definitely matters. So because we said 15 feet to 7 yards, 15 feet is your first term, 7 yards is your second term. This answer obviously would be different if we had the reverse. If we had 7 yards to 15 feet, then our reduced answer, our converted and reduced answer becomes 7:5 instead of 5:7. So you want to be really careful. Order definitely matters when referencing ratios. Let's do one more. So we have 5 days to 80 hours. I want you to take 60 seconds to go through the steps that we have just outlined in order to find its respective reduced ratio. 60 seconds starting now. All right, excellent work. We have a bunch of answers coming through the chat, and it seems like everyone is in agreement. So first things first, we have 5 days, 80 hours. We want to consider, what is the relationship between days and hours? Yes, Patrick, Maria, Kayla, Doc, excellent. So let's say in one day, there's 24 hours. Okay, so we want to consider which one we want to convert. If in one day is 24 hours, 2 days there's 48 hours, well, let's convert the days then. So essentially we have 5 days, each day has 24 hours, that means in 5 we have 120 hours. So now we write it as 120 hours to 80 hours. They're the same unit of measurement. Think of this as a fraction, just like we have before. We notice right off the bat the zeros will cancel because you're essentially dividing by 10. And then we have 12 over 8, and we could say, wait, we definitely can reduce more. If we divide both of these by a 4, that leaves us with 3 over 2, which then means that our reduced ratio is 3 to 2. Excellent work. Everyone is in agreement. That was beautiful. Moving right along. A proportion is a statement of equality between two ratios. Now, if you think of a ratio instead of as A to B with a colon, but a ratio as a fraction, A to B, then a statement of equality between two ratios, here's one ratio and here's the second ratio. That is a proportion, okay? So essentially a proportion is when you have a fraction equal to another fraction. Mind you, it could be a whole number equal to a fraction because every whole number can be written over a 1. So you can essentially manipulate that to look like it's a statement of equality between two ratios, otherwise known as a proportion. Consider that in order to solve a proportion, we could multiply both sides by the LCD, or we can cross multiply. Okay, in this case, you can cross multiply. You'd be multiplying the means and extremes. So essentially, here's what it would look like. A times D, B times C. Now keep in mind, this is an equation. So essentially what you would have is A times D is equal to, and then you multiply the other side, B times C. Now the location of those products doesn't matter. It could be B times C equals A times D. But for the sake of, simplicity, I simply wrote A times D is equal to B times C. All right, so let's use a proportion to solve the following word problems. The ratio of blue marbles to red marbles. Now that's very specific. Blue marbles to red marbles. So essentially what it looks like is blue to red. That's going to be really helpful. And that ratio is 3 to 5. So right underneath, I'm going to write down that the ratio of blue to red is 3 to 5. You're then told that there are 212 blue marbles. How many red marbles? Okay, so because we have 3 pieces of information, we're missing the 4th, right? Notice we're talking about blue and red. So blue, red. That's kind of an indication that, hey, wait a second, we're talking about a proportion. It's a statement of equality between two ratios. So we can say blue to red is equal to blue to red. And instead of a question mark, I'm going to put capital R because we are trying to determine the number of red marbles. I hope this concept of writing a proportion is clear. Again, one of the things that I can say is you should consider that it is a proportion if you're noticing that your units appear twice. So meaning blue marbles, red marbles, blue marbles, red marbles, right? Like they're appearing twice. So there's something that's happening here. We're essentially trying to create some sort of equivalent fraction. then consider that you have 4 values, 3 of them are known, right? The fourth one is unknown. So we had blue to red, blue, I don't know, right? So we had 1, 2, 3 pieces of information, but we were missing the fourth. So those two things combined indicate that, yes, we're definitely looking at a proportion here. So once we set up our proportion, we can go ahead and cross multiply. So we have 3 times r, which is 3r, and we have 5 times 212, which is going to give us 1060. So far, so good. At this point, because we have 3 times r is equal to 1060, we want to solve for r by dividing by 3. So we divide both sides by 3. And when we plug this in, we know we're not going to get a whole number. We actually got 353.3 repeating. But it's a word problem. And the word problem asks, how many red marbles are there? I mean, I guess you could be pretty, I don't know, slick and say, oh, you have 353 marbles and a third of another one, right? So a broken marble. I mean, if you wrote that, I would totally be like, yeah, okay, you're right. That's hilarious and you're totally correct. So Kayla mentioned, in this case, you may just want to round it. I would not round up on any broken piece. I would simply cut off the change. So for instance, if this were 353.7, I still wouldn't round up because that 0.7 means you have a broken piece of marble, okay? And that broken piece of marble, you're not going to count as a whole marble. So my answer would be, there are 353 red marbles. Again, even if that said 353.5 or 0.6 or 0.7 or 0.8 or 0.9, I still wouldn't round up to 354 because there weren't 354 red marbles. There were only 353. That point whatever basically refers to a broken marble. Awesome. Let's turn the page. A person who is 6 feet tall casts a shadow that is 2.6 feet long. And Doc, you're exactly right. A partial marble is not going to roll. So you can't play any of those games that you typically play with marbles. So why would you want a broken marble? You'd be like, oh, what is this? Okay. A person who is 6 feet tall casts a shadow that is 2.6 feet long. At the same time, a building casts a shadow that is 87.5 feet long. How tall is the building? So one of the things you may want to get into the habit of doing is collecting the information that you have. So we know that we have a person. And we know that the person is 6 feet tall. And we know that for that person, that the shadow is 2.6 feet long, right? So the person's 6 feet tall and the shadow's 2.6 feet. But let's go to the building and write down that information. So a building casts a shadow that is 87.5 feet long. So we actually don't know the height of the building. So I'm going to say question mark feet tall. But we do know that the shadow, it is 87.5 feet long. So that's pretty much a good strategy to start off with by kind of organizing what we see. We have 1, 2, 3 values. We're actually missing a fourth. Notice we have the height of the person, the shadow, the height of the building, the shadow. So notice these units are coming in as doubles. So we are seeing shadow, shadow, height, height twice. And we're also recognizing we have 3 pieces of information out of the 4. So we are looking for the fourth one. Again, that's an indication that, okay, we definitely have a proportion here. So we can start with the person. So they're 6 feet tall with a shadow of 2.6 feet. And that's going to be equal to the height of the building, which I'll call capital B. We don't know what it is, but the shadow is 87.5 feet. Notice height of the person, length of the shadow. Height of the building, length of the shadow. You have to be consistent when you write out your proportions. You don't want to mix and match the location of this information. You could have said, if you wanted to, you could have said 6 over B is equal to 2.6 over 87.5, because essentially that would be height of the person, height of the building, shadow of the person, shadow of the building. So think about being consistent when you write out your proportions, and I'm going to make that a note here. Make sure you are consistent in your proportions. Okay, we can certainly write several other proportions if we wanted to. Just make sure that you're consistent. At this point, we're going to go ahead and cross multiply. So we have 6 times 87.5, and I'm going to grab my calculator and punch that in. 6 times 87.5 gives us 525 is equal to, and then in our second product here, we have 2.6 times B, so it's 2.6B. Excellent, Kayla. Let's take a look and see if that's correct. We're going to isolate B by dividing by 2.6. And when we take the 525 and we divide it by 2.6, we get 201.923. And I'm actually going to write a bunch of these values. 201.923 ... Now, we can say that this building is 201 feet, but the really amazing thing about length, measuring in length, is that it is continuous. It's not discrete. So what I mean by that is you can have 201.9 feet. That's more specific and it's closer to what it actually is. And that is only the case when you have measurements that are continuous. Think of that logically. So when you talk about a height of a person, you could be, like you might say, I might say 5'7", right? I'm pretty close to 5'7", but I know I'm not exactly 5'7", right? So if I wanted to be super, super, super specific, I might like actually take a measurement and then, give you the value in terms of like inches or centimeters or something like that. And I could be way more specific. But the idea here is that because length is continuous, meaning you can have decimal values, then we want to be as specific as possible. When we had the marble word problem, our answers were going to be discrete because you don't want to have part of a marble. That really doesn't make sense to say, here's, however many marbles plus, this broken one here, take it, it's yours, right? So we just want to be careful with that idea of, are these going to be whole values or can it actually be a decimal? For instance, let's say we were trying to find the temperature outside. Temperature is also continuous. You can have a decimal when you talk about the temperature that is outside. Typically we don't, but you can. You certainly can. So think about that logically as you move through some of these problems. Think, am I going to round here? Am I talking about an object? Am I talking about people, right? Am I going to have 15.1 people? No, don't do it. That's scary, right? That's pretty scary and creepy. You'll have 15. So you just really have to think about this logically. Can have a decimal for this particular unit of measurement. Oh yeah, I know what that means. Okay, we're going to write that. So for this problem, I would actually say the building is 201.9 feet tall. You could be even more specific by saying 201.92, or even more specific, it's up to you. I'm going to round to the nearest tenths. Okay, let's take a look. The building is 201.9 feet tall. Okay, We can be very specific in this case. Beautiful. Let's take a look at number 3. We have b plus 6 over 5 is equal to 2b minus 1 over 4. We definitely have a proportion here. We have a fraction equal to a fraction. So our terms equal to, so essentially like a over b is equal to c over d, right? This is definitely a proportion. So we are going to cross multiply in this case. And I'm going to circle these carefully just so you could see them. So in our first bubble, we have b plus 6 times 4. Now, please, please, please write this correctly. B plus 6 goes together. You are going to package the pair of terms in parentheses. Did you hear that? Package the pair in parentheses. You like that alliteration. Package the pair of terms in parentheses. The b plus 6 go together, package them. Okay? Because we're multiplying by 4, let's throw that right in front as the coefficient. It's an easy way for us to see. We could have written b plus 6 times 4 with the 4 outside, and we'd still have to distribute the 4. But I like putting the coefficient in front of the quantity because that's typically what we should do. Bring our equals, and then we have 5 times 2b minus 1. Again, 2b minus 1 is the pair of terms that must be packaged. 2b minus 1, they go together, package them up. And they're being multiplied by 5. That is how you would want to write out your equation when you cross multiply. And again, we are only allowed to cross multiply because we have a proportion. Fraction equal to a fraction. You cannot cross multiply across addition or subtraction of fractions. Please don't do it. And you cannot cross multiply across multiplication or division of fraction. Please don't do it. Those are totally different sets of rules. Cross multiplication is only going to refer to proportions. All right, let's solve. So in this case, we are going to distribute. 4 times b is 4b. 4 times positive 6 is positive 24. Bring down your equals. 5 times 2b is 10b. 5 times negative 1 is negative 5. Awesome. At this point, we're going to move our variable terms first, not our constants. I have a 4b and a 10b. I think I'm going to move the 4b over to the 10b. So we have a positive 4b. We're going to use the opposite operation, which is to subtract it. So we subtract the 4b from both sides. 4b take away 4b is 0. But 0 plus 24 is still 24. So I'm just going to write 24 instead of 0 plus 24. 10b minus 4b is 6b. Bring down the minus 5. Next, we're going to bring the negative 5 over to the 24 by adding it. So we add 5, opposite operation to bring to the opposite side of the equals. 24 plus 5 is 29, is equal to, we'll bring down the 6b. Negative 5 plus 5 is 0. They cancel each other out because they're opposites. 6b plus 0 is still 6b. Last but not least, we have 6 times b, so we must divide by 6 on both sides. And voila, we find that b is equal to 29 over 6. This fraction cannot be reduced, so that's totally cool. We're going to leave it 29/6. We are not going to write it as a decimal because I really want you all to get used to leaving your answers, if they're in fraction form, leave them in reduced fraction form. The only time you should have a decimal is if your original problem starts with a decimal, like number 2. You see how we had decimals in our actual word problem? So our answer could also be a decimal. Let that be a clue for you. Number 4, we have 11m plus 7 over 2 is equal to 8m minus 3. Go ahead and solve this. Let's see what you all come up with. All right, you are all doing phenomenal work. Let's take a look. So right away, this doesn't look like it is a proportion, but I'm betting that you all said, wait a second, I could put the 8m minus 3 all over a 1. So if I rewrite this as 11m plus 7 over 2 equals 8m minus 3 over 1, I can now cross multiply because it is a proportion. So we're going to do exactly that. So we have 11m plus 7 times 1, which is simply 11m plus 7. I would write parentheses 1 in there, but I want you to just be critical as you move through this. 11m plus 7 times 1 stays 11m plus 7. Don't overthink it. Next, we have our 2 times 8m minus 3. 8m minus 3 is the pair of terms. They get packaged in parentheses, so keep them together. At this point, we are going to distribute. We have 11m plus 7 is equal to 16m minus 6. We are going to move the variable terms first. So I'm actually going to move the 11m over to the 16m just to make life easier. So this is a positive 11m, which means I'm going to subtract it. And these cancel, leaving me with 0. 0 plus 7 is still 7. 16m minus 11m is 5m, and then we have minus 6. Next, I'm going to bring the 6 over to the left-hand side. So 7 plus 6 is 13, is equal to 5m. Notice these terms are opposites. They cancel, leaving us with 0, but 0 plus 5m stays 5m. At this point, I divide by 5 to get m completely by itself. 5 divided by 5 is 1. So 1m is still m, and m is equal to 13/5. So excellent work, everyone, on this problem. I do want to quickly show you what it looks like if we did not recognize that this was a proportion by placing the right-hand side of the equation over 1. Check this out. Let's say instead I go back. I say 11m plus 7 over 2 is equal to 8m minus 3. I can say, well, I do have 3 terms. Here's my first term, 11m plus 7 over 2. My second term, 8m. And my third term, negative 3. What if instead I wanted to simply use the LCD, just like we have in the past? What if instead I'd simply want to multiply by the LCD, which is 2? So in this first term, I notice numerator, denominator, 2 divides into 2, leaving us with 1s. But 1 times 11m plus 7 is simply 11m plus 7. Then I have 2 times 8m, which is 16m. And now I have negative 3 times 2, which is negative 6. Take a look at these equations. Regardless of the approach we took, we ended up with the same linear equation. So it's very important that you all recognize that you have different strategies that you can certainly apply here. Don't feel like you have to be pigeonholed into one strategy and one strategy alone. We can play around with the things and the tools that we have to make sure that we're flexing those math muscles. Okay? I would continue solving this, but it's right there. So I'm not going to. All right, last page. This is it, page 17. We are going to quickly talk about similar figures. Similar figures are cool. Essentially, what figures are similar if their corresponding angles are equal and their corresponding sides are in proportion. So I have an example here, solve for the missing side. It's blank because I want to draw it with you. So let's go ahead and draw a small triangle that looks like that. Okay. And then let's call this A, B, C. And then we're going to draw another triangle that looks identical, except make it seem like you made it super big. You enlarged it. And we'll call that D, E, F. Yes, Doc, that's awesome. See, you're trying different avenues and you're getting the same thing because you're still applying the rules for solving linear equations. That'll never change. So in this case, triangle ABC is similar to triangle DEF. Okay? So what I want us to do right now is let's label a couple sides. So let's say that side AB is 4.3 inches. And let's say that side BC is, let's say, 5.1 inches. All right. Next, I'm going to say that side DE is 11.8 inches, and we're going to say that side FE is unknown. And we can call it any variable you want. I'm just going to draw a question mark here. Because these are similar figures, right? And because our corresponding sides are in proportion, we can actually write out a proportion to solve for the missing side. So we would like to come up with a proportion. We can say 4.3 over 5.1. So top side, bottom side of the small triangle is equal to top side, bottom side of the small triangle, or the large triangle. Do you see how we have top over bottom, top over bottom? We are consistent in our setup of our proportion. That's just one proportion. I'm going to write another one just so you could see how we can play around with this. What if instead you wanted to say 4.3 over 11.8, right? Top, top. That means you have to be consistent. Bottom, bottom. So 5.1 over unknown, the measurement of that side. So top little triangle, top big triangle. Bottom little triangle, bottom big triangle, right? You see the consistency here? Let's do one more. Maybe we'll start here and we'll say the bottom of the big triangle, the top of the big triangle. That means we got to do bottom of the little triangle, top of the big triangle. In each of these proportions that we've written out, they are all consistent. We made sure that we correctly placed everything in its respective location. We didn't crisscross any of this information. So regardless of which proportion you take, it doesn't matter. We are going to cross multiply. We have 4.3 times m. And we have 11.8 times 5.1. So 11.8 times 5.1 is going to give us 60.18. In this case, we are then going to solve for m by dividing by 4.3. We have m is equal to, so 60.18 divided by 4.3 is going to give us, ooh, this is a good one. I'm actually going to leave it to 3 decimal places because if you notice in your calculator, you get 13.9953. So just for the sake of being, different, I'm going to write 13.995 inches. Some of you may say, oh, come on, Dr. Santiago, let's just say 14.0, right? But, I want to be difficult, so I want to write 13.995. So that way I'm as close to as accurate as possible. Just a little side note, if you wanted to write a statement that says triangle ABC is similar to triangle DEF, then you would write it this way. Triangle ABC is similar to triangle DEF. Kind of cool, right? Maybe it brings you back to your geometry class days when you did geometry proofs. But either way, just something so you have, just for your knowledge. Okay? And that concludes our notes. So it's a brief discussion on similar figures because we really don't do too much with it. I essentially want to give you exposure so that if you're told that two figures are similar, you can set up a proportion to solve for the missing side. Typically, we do not look at solving angles for the angles in this particular class. We strictly look at the lengths of the sides. I will see you all on Monday. I want to say Excellent work to everyone today, and have a fantastic weekend. Bye.